Hello and welcome back to an introduction to the Wolfram programming language. Today I will be covering my favorite topic in the Wolfram programming language, replacement rules. Replacement rules are typically done with the function replace or replace all or replace repeated. In this case, I'm using replace all. I have my list of rules here, read this way. When I see x, it will be immediately replaced by the evaluated value 2. When I see y, it shall be instantly replaced and evaluated with 3. Now if I run this, just having my input argument as hold form, which will simply prevent this from evaluating, x squared plus y squared, I end up with x being replaced with 2 and y being replaced with 3, just as it had said. Now if I want to be faster, I can write the syntactical form, which this means replace all, simply a forward slash and a period. And then I have my list of rules, which x is being replaced by 2 still, and y is still being replaced with 3. If I run this, I get 13 because 2 squared plus 3 squared is 13. I can even replace function heads. It's rather useful if I'm trying to manipulate particular functions and arguments. I can even use this for differential equations, which I did in another notebook, and will further detail after this video. If I run this, I end up with the first derivative being replaced with EQN y sub t 1, because I told it to find derivatives of some argument here of y of t and to replace it with EQN y of t and then my argument pattern that I specified here in. Now in got replaced with 1 because of the first derivative. 2 was replaced here because this is the second derivative. And this was not replaced because it does not fit this pattern form. This is not a derivative. Now I can even make a list, an empty list beforehand, and say that, well, whenever I see a product between something and a derivative, I'm going to append to the empty list u, where u is the coefficient of the derivative, and n, where n means the number of derivatives. And if I were to find out what is in this list, I get that b is the coefficient of the first derivative and c is the coefficient of the second derivative. I can even use this in functions, like dir here. If I run dir of sine of t cubed of the variable t and I wish to replace it with pi, I can. Simply put, I differentiated the function with respect to the given variable, and then after that I replace the variable with the second argument. I can replace with t if I want to, so that I still have an equation. I can even do repeated replacements. This syntactical form of replace repeated, which runs through this list until it cannot replace anymore. The first time it'll run through, x will be replaced with y will be replaced with z, and z shall be replaced with capital I, which is the imaginary unit in the Wolfram programming language. And then it shall run through it again. X being changed to y shall be changed to z. This will be changed from z to I, and this will still be just I squared. Then run through it a third time. This z shall be replaced with I squared, and you'll have nothing but I squareds. It'll then run through it a fourth time, find that nothing was replaced, and then terminate. And in the end, I shall end up with -3 because I squared is -1. -1 plus -1 plus -1 is -3. I can even create a function that whenever I decide to make a declaration within said function, it will make it so that it replaces the function head set or set delayed with lowercase set or set d. Now let's say I put y equals 2 and x is set delayed as 3, and for the heck of it, 2 plus 2. As you can see, y, because this is a function here, the function being set y comma 2, set here is replaced with a lowercase set, and set delayed, which is this function, shall be replaced with set d. And then 2 plus 2 is unchanged. Now, if you remember from a previous video for detailing functions, I was able to make a function that was going to build Pascal's triangle. I can build this same function more efficiently using replacement rules. Instead of having a little more complicated version of a list manipulation, I can simply change the list into a product. So ABC is simply changed into the actual product. Same with ABCD and ABCDE. Same as before, an infinite sequence may be placed in the function and it shall return like this. And even here, I have a form for the series e to the t, and if I run it, I'll have this. Now if I were to replace t with 3 and then take the natural logarithm of it, I will get 3 back. Logarithm of percent meaning this is going to be the last output from Mathematica, and I'm going to replace t with 3. And because it'll try to do it in an exact form, I'm going to use in to make it a decimal. And I get 2.9999876. I can even get more specific with conditions. This meaning condition. If it's true, it'll go through. If it's false, it will not. Let's say I have some pattern where two things are multiplying. Let's say that A, which can be either one of these, or even if I put B, it'll still work. A has to be a number. If it is a number, it'll be true and it will go through and replace A with 2 times A and replace B with B. So if I run this, I will get 4 times x plus 8 times x squared. Or, if I really wanted to, I could put a squared. 2 squared is 4, 4 squared is 16. And if there is an instance where I try to use replace repeated and a loop will occur, it will terminate. And if there are circumstances where you wish to do multiple replacements, you can specify a list of rules within the original list, and it will return a list of outputs. If I replace x with 3 and y with 7, 3 plus 7 is 10. If I replace x with -4 plus 3i and y with 4 minus 3i, I get 0. And if I replace x with z and y with z, I get 2z back. And Another point to make is that it will read specifically from left to right, meaning that even though it will still evaluate, as you would expect, x being replaced with 1 and x being replaced with 3 will not be evaluated because this was the first rule. Now, if I wanted to evaluate, I will have to specify by making each one another list. And as you might expect in the end, I get a list of results. All x's are replaced with 2, all x's are replaced with 1, and as you might notice, 1 to the n simplified to 1, and x was replaced with 3. Anyways, I hope this clarifies how useful replacement rules are in the Wolfram programming language. Have a great day.